Hi guys. All right, so we are starting Unit 6, which feels kind of like a hodgepodge of different things, but they all actually go together. But we're going to talk about naming, bond types, bonding and bond types, excuse me, and then shapes of molecules, because that is how you determine the state of matter of these different compounds when they form molecules. So on the screen right now, I have a periodic table. And it should look pretty similar to the one that I had you color in class the other day. And I have the three main groups. I know you have the metalloids also on yours, but I've kind of the three main groups because this is how we'll look at naming in particular. And so I have in my green, I have the metals with known oxidation numbers, and that's going to be big in a minute. I'll write that on here with known ox numbers. So we know always if they're a +1 or a +2, +3 kind of a thing. And then in the red above the zigzag, so remember the zigzag is, right in here. Oh, let's see. And so it keeps on kind of going there, but this is the separation between metals and nonmetals. So my reds are the nonmetals, and then the purple section are the transition metals. And notice that even over here in, pick a color that'll kind of stand out here, in this little section down here, even though they're in the columns when we talked about those having the known oxidation numbers, because of the way that they are kind of divided by that zigzag, they end up being transition. And remember what that means is that their oxidation numbers or their number of valence electrons changes depending on what form you're looking at of that element or what compound it is trying to form. Okay, so we are going to name things, and this should be kind of a review of something that we talked about when you all were in physical science and the chemistry semester of that. We'll add some stuff to it, so it won't all be completely the same as what you remember, but it should be somewhat similar. All right, so our first type of compound are going to be the binary ionic compounds, which means you're looking at a metal, and very specifically a metal with a known oxidation number and a nonmetal. So something from the left side of the periodic table and then something from the right. When you name this, you name the metal just like normal. You don't change anything about it. So you have the metal name and then you have the nonmetal name, but you change the ending to IDE. So most of these are going to change from like an EN ending like oxygen, or an INE ending like chlorine, and it becomes an IDE ending. And so very straight format. This again, you guys should probably remember, and it should sound somewhat familiar to you. So that first example, NaCl. Na is sodium. I'm going to try and write on here. It's kind of hard and messy, so I apologize for that. Let's see, you have sodium. And then Cl is chlorine, but remember that becomes chloride because we change the ending. All right, then the next one, MgBr2. Oh, excuse my little typo there. That little 2 should be a little subscript 2. All right, so MgBr2. Mg is magnesium, so don't change anything about that. And then the Br, the 2 I ignore in this situation. I'm just worried about the Br. And so that is bromine, but it becomes, when I change the ending, bromide. Okay, now we also need to be able to go from the name back to the symbol or the formula for that compound. And so this is where we deal with oxidation numbers. In an ionic compound, the oxidation numbers, the positives for the metals, the negatives for the nonmetals, will need to equal out to 0. And that's when we add in little subscripts, if needed, to change the number of atoms that we have so that we will end up equaling 0. Once you get used to the system, super duper easy. So we'll do the first one. So calcium oxide, the symbol for calcium is Ca. And this was one of the things that we either will label, or I think I maybe have already had you label it on your periodic table. But the column that Ca is in, it's an alkaline earth metal. Those have a +2 oxidation number. So I'm going to put a little 2 above that calcium. And then oxide. So this is oxygen. Remember, it's been changed because of the naming format. Oxygen is, or oxide, excuse me, is just O, and it is in the -2 column. And so what you're looking at is these numbers now. Do they equal 0? And they do. So when you write that formula, you don't really change anything. You just put CaO. And that's it. That's the formula for calcium oxide. All right, so now lithium sulfide, pardon me, is going to be one where we have to do a little bit with the numbers. So lithium is Li. It has a +1 oxidation number because it's an alkali metal. It's in the first column. And then sulfide is sulfur. So there's my S. And it is right underneath oxygen, so it's also going to have a -2. So now I've got a +1 and a -2. That doesn't equal 0. And so you want to figure out, okay, what can I change? What's the easiest way to get to equal 0? The easiest way is to have 2 lithiums, is to have 2 Li's. And so when you write that formula, you would have Li and you'd put a little subscript 2 S. If there's no number with the symbol, like the S has nothing after it, there's an assumed 1 there. And so now essentially what I'm saying is +1, and then still my -2. And so that equals the 0. Very often you might hear people talk about the crossover method. Works almost all of the time correctly. The crossover method says that you take just the number, not the negative, of the symbols, and you just cross them over to the other element. And so the 2 from the sulfur will cross over to the lithium, and the 1 will cross over to the sulfide, so that's you get Li2S. In very rare cases, that doesn't work automatically. You may have to reduce your oxidation numbers, which I know sounds confusing. What in the world am I talking about? But we'll do examples in class, and you'll get the hang of it, I promise you. Okay, so now the next type of binary ionic compound involves a transition metal. So transition metal are the purple ones on my periodic table, kind of the big middle section. They need a Roman numeral in the name in order to tell the oxidation number for that transition metal. So you add a little bit to it. Oh, I have another typo here. This little 2 should be a little subscript 2. Sorry about that. So you have the metal name staying the same, but now we put a Roman numeral after it with the non-metal name. All right, so now that first one, you've got Cu. Cu is copper. So Copper. And then I always put a set of parentheses, and then I go on and name my other element. O is oxygen, which becomes oxide. So now here's the deal with the transitions. We have to figure out what it is based on the compound that it is in. So I don't know copper because it's transition, but I do know oxygen. Oxygen, we've already said on the previous page, has a -2 oxidation number. In order for copper to equal out or to zero out with that oxygen, with that -2, I have 1 copper. Notice it doesn't have any subscripts after it. I have 1 copper. That means that its oxidation number is going to have to be a +2 so that they will equal 0. So in my little set of parentheses there, I would put a Roman numeral 2. Okay, so now the next one, I've got some subscripts in this one, so that makes it a little bit different, but start out the same. Fe is iron. And then I put my little parentheses. And then Cl is chlorine. Of course, that becomes chloride. All right, and so now I have an unknown with the iron. It's transition, so I don't know what its oxidation number is. But I do know that Cl individually there is a -1, but I have 2 of them. So that again is like saying -1, -1. So what does iron have to be in order to make that equal 0? I just have one iron that doesn't have any subscripts with it. So it will have to also be a +2 like the Cu was in our other example. So now +2 -1 -1 equals my 0. And so I have another Roman numeral 2. Now, and I don't have any examples of writing it the other way, writing the formula instead, but it works just the same way. The only thing that you have to remember is this Roman numeral applies to the metal that is in front of it. So that Roman numeral in that case is telling me, like I have written there already, is telling me that iron has a +2 charge. Okay, so now here are the first part of our next type of compound that we're going to name polyatomic compounds. Polyatomic compounds contain polyatomic ions, and I have listed here probably the more common polyatomic ions. There are others that you'll see, but these are the common ones. These are what are on the posters up above the smartboard in our classroom. And these act like individual atoms, and they bond with other elements or they bond with other polyatomic ions and form what are known as the polyatomic compounds. So when you work with these, you don't look at the individual atoms that are made up or that they're made up of. You look at the compound as a whole or the ion as a whole, and then you go through the process just like we did on the previous examples. Okay, so now there are some relatives that I want you to know about. You're not going to need to memorize any of these, and as a matter of fact, I'll have you write the polyatomics from the page before on your periodic table, but I did want to make you aware of these relatives. The polyatomic ions can change. The first group of relatives change if you have a different number of oxygen. So if you have one less oxygen than the original, for example, that first one, nitrite, is a relative of nitrate, which is NO3. Still a -1, but when you lose that one oxygen, you change the ending. The ending becomes an ite. And so that's what this is the first set of relatives. And we'll do some examples here in a minute, just in case you're wondering about that. All right, a second class or group of relatives is if you add hydrogen. So if you take the polyatomic and you add hydrogen in front of it, then it adds hydrogen to the name, and then you reduce the charge by 1. And again, reducing charge is a little bit different because you're reducing a negative. But so that first one is the relative of carbonate, CO3. It has a -2 charge, but when you add the hydrogen in, it becomes hydrogen carbonate, and you go from a -2 charge down to that -1. That's because hydrogen is a +1, and so -2, you add the +1, that's where you get the -1. Okay, so here are some examples. I'm not going to do all of these just for time's sake, but I do want you to see kind of what we're talking about with naming them. And I like these. You don't have to change. Usually you don't have to change the endings. You don't really have to do anything. You just name the parts. And so, for example, that first one, NaNO3. One thing you need to train your mind to do is, if there's not parentheses around the polyatomic, to recognize it. And so I always tell my students, if you want to go ahead and put parentheses around the polyatomic so that you see it, doesn't change anything. You still have the right thing, and that might make it a little bit easier for you to name it. Okay, so Na is sodium. So sodium. And then NO3, you name as one thing, it is nitrate. Okay. Occasionally I have students who will try and name it individually. Don't. That's a polyatomic. You want to name it by its name. All right, the next one, NH4 parentheses 2S. So NH4 is already in parentheses, so that's the one that it tells you that it's a polyatomic, and it is ammonium. And then this is the one little glitch to the you don't have to change anything statement that I just made. S is sulfur, but you still want to change it to the IDE ending like we've been doing with the previous compound. So it is an ammonium sulfide. All right, and then I'm going to jump down and do a couple of the formulas. So copper 2 sulfate, notice Roman numerals 2, that tells you that it is a transition metal. The Roman numeral 2 tells you that copper is a +2. So I will have Cu, and I will go ahead and put my +2 there so that we remember that. And then sulfate, the ATE ending tells you, look at the polyatomics. Sulfate is SO4, and it is also a -2 charge. So when you write that compound's formula, you just have CuSO4. You can put parentheses around the SO4 if you want, but you don't need to. That next one, let me see what's a good one. Well, we'll go ahead and do the next one. Ammonium hydroxide. That's when you have 2 polyatomics, and actually hydroxide is kind of a tricky one. That "ide" ending doesn't stand out as much as the H, so you're just going to have to remember it. But ammonium is NH4, and it's a -1, and hydroxide is OH, and ammonium is +1, and then hydroxide is a -1. So again, you don't really have to do anything. You just have to put them together. NH4OH. You want to keep them separate. Don't combine the H's. Don't, rearrange everything. Just, write the formula like the name is written. Okay, now here are, good grief, I'm sorry, I messed up and didn't put my little subscripts in here. So that's a little 2, and that's a little 3, that's a little 4. All right, so now binary covalent compounds. So nonmetal plus nonmetal. So that basically means you have both elements from the right side of the zigzag line that we talked about. So with these, you don't have to worry about oxidation numbers, which is nice. You don't have to worry about the positives or negatives. And you just basically write what the formula tells you. And the numbers are going to be given as prefixes if you're seeing the full name, or you'll write them as prefixes if you're writing out from the formula. All right, so from the next one, sorry, my phone's ringing. So for that first example, you have N2O3. And so I have a list of prefixes over to the side, and they are, we'll go up to 10. There are bigger than that, but we'll just go up to 10. And then you put the prefixes in. So if I have N2O3, the 2, I'm going to use di, because that is the prefix. So I would have di-nitrogen. I just put the prefix right in front of the name. Don't change anything. Don't do anything with the ending. So it's di-nitrogen. And then O3 is trioxide. All right. I'm already almost 20 minutes into this, so I'm going to speed it up a little bit, and we'll just do the third example. So then if I'm going from the name to the symbol, I don't have to worry about oxidation numbers. I just write what it tells me. So triphosphorus tells me phosphorus is P, and I have 3 of them. And then hexasulfide, sulfide is sulfur, and hexa is 6. Now, generally, that looks like you could reduce it, which you could, but in general, you don't with these because it's usually a bigger structure than what we're used to. So you just kind of keep everything the same. Okay, so now moving on to the compounds. So we're going to look at ionic versus covalent compounds. And with some of these characteristics we've already talked about, but some may be a little bit we haven't really mentioned them. But first off, with bonds, ionic compounds transfer electrons. One gains and one loses, and so you have a positive, negative charge or oxidation number, and that's why they bond together. Covalent compounds share electrons, which means the electrons are between the two atoms being shared within their orbits, and so that holds them together. Ionic compounds are composed of metals and nonmetals. Covalents, in general, two or more nonmetals. They're usually bigger compounds. Ionic compounds are solids. Covalent compounds can be any state of matter. Ionic compounds have a very high melting point, usually over 300 degrees Celsius, while covalent have a much lower, so less than 300 degrees. Solubility in water kind of depends. Ionics are high in this. Covalent, it depends on the type or the usually the state of matter. And then electrical conductivity, if you dissolve these in water. Ionics are good conductors in water. Covalents are either very poor, very small, weak current can be carried, or none at all. Kind of the typical, to me, ionic compound, that if you want to kind of think about it this way, is salt, like table salt. And so, so if you kind of think about that, on some of them, it could help you kind of picture it. You know, salt's a solid. I don't know if you've ever tried to just heat up salt. It doesn't melt, but it dissolves easily. It's a good conductor. Covalent compound would be something like sugar. So again, it is a solid, but it does melt at a very low temperature. It is actually very soluble, but it's a non-conductor. And so we talked about all these things when you guys were freshmen, so if I'm repeating, sorry about that, but if I'm reminding, you're welcome. Okay, so now predicting bond types. This depends on electronegativity. And so when we talked about electronegativity, when we talked about the periodic trends, and this tells you how easily an atom wants to gain an electron, or how attractive it is to the element is to the electrons. Remember, this is pretty flow, has the highest electronegativity. And so depending on the actual electronegativity numbers, excuse me, and I'll give you a chart, and I'll have one on my next screen. You can actually determine the type of bond if you know the electronegativity values. The difference between the electronegativity of the two elements in the bond help you determine the type of bond. And so there are ranges. If you subtract your two numbers and you get 0 to 0.4, you have a nonpolar bond, which sometimes is called pure covalent, where the electrons are shared equally. If you get a difference of 0.5 to 1.6, it's considered polar covalent, which is an unequal sharing, which means the electrons are closer, or more of the electrons are closer to one atom versus the other. And so, but they are still held together. Or if you get a value that is greater than or equal to 1.7, you have an ionic bond, which is a complete transfer. One atom will give up its electrons and become positive. One atom will gain the electrons and become negative, and so the positive negative holds them together. So the chart. So here's the chart. When I give it to you, it's going to be all on one. There'll be several charts on here, but the top chart is the electronegativity chart. Notice that it looks like the periodic table somewhat, but it doesn't have the noble gases. Remember, they don't form bonds under normal circumstances, and so it ends over here with the halogens. And look right there. There is pretty flow, and if you look at her electronegativity value, I know she's not really a she, but it makes me feel better to say it. If you look at those electronegativity values, she has, or fluorine has, the highest value of all. Okay, so that is the trend. And for the most part, again, the trend is that as you go this way on the periodic table, electronegativity is going to increase. Okay, so this is an assignment that I'm actually going to give you, and we'll kind of go through it. But we'll do this first one, and so you have BCl3. And so the two different elements are boron and chlorine, and so you're going to subtract the difference between the two. You can do electronegative, or excuse me, you can do absolute value, and so the value for boron, so if you look on that chart, and you'll have one in front of you to always use, boron has an electronegativity value of 2, and chlorine has an electronegativity value of 3. So there's the 3, or maybe, okay. And so we've got our electronegativity values. Notice there's a little subscript 3 on chlorine. You ignore that. You're just looking at the two elements. And so the absolute value of 2 minus 3 is 1. And so if you think back to the ranges that we just talked about, that middle range, the 0.5 to 1.6, is the polar covalent. And so this is held together by a polar covalent bond. Okay, so now, why do atoms bond? They bond because they want to be like the noble gases. They want to have 8 electrons in their outer shell, and they can do this by sharing or by gaining or losing. And the Lewis dot structures are used to represent the electrons that are being shared. And we did a form of this when you guys were freshmen, and so it should be somewhat familiar. But when you are looking at your elements, you look at the valence electrons. So if we're talking about HCl, which is hydrochloric acid, hydrogen is in the first column, and it will always have 1 dot. Chlorine is in the 7th column, or the 17th column, depending on which numbering system you're using. So it will have 7 dots. 1, 2, 3, 4, 5, 6, 7. And so then when you put them together, it's probably, hopefully, pretty easy to see that hydrogen will give up its 1 electron, and chlorine will take it, but they will be bound together by that transfer. And so when you draw this, you'll draw, I'm going to draw them kind of in color so you can see it. You're going to draw the hydrogen, and there's its 1 electron, and then the chlorine with its 7. Oh, my dots are getting smaller. Those 2 dots. Okay, and then another dot. And so they are held together basically by that bond. That is the representation. It looks a little different in the real world, obviously, but that is the representation of it. For the next one, NH3. So NH3, N has 5 dots. It is in the 5A, or the 15th column. And then we've already talked about hydrogen. Each hydrogen has 1 electron. And so again, remember, we're talking 8 is kind of the magic number. So nitrogen will have its 5 dots. And then each hydrogen will fit in on a side and contribute an electron so that they will bond together. Nitrogen has its 8 electrons, so it is the one that is achieving the noble gas configuration. Hydrogen is a contributor to that. Hydrogen actually meets what they sometimes call the duet rule, and it's happy with 2 electrons. So if it is sharing or adjacent to 2 electrons, it is full. All right. So now, the 3 main characteristics, so now we're getting more into how the actual atoms react and compounds form, all that kind of stuff, are shape, polarity, and then state of matter. So the shape. The shape depends on, or we use what they call the valence shell electron pair repulsion theory, which is called a lot of times, or at least I've always heard it called the Vesper theory, even though it looks like Vesper. Vesper is what you'll probably hear, and it is based on mainly on the bonding pairs here and the lone pairs down here, but the bonding pairs are the electrons that are being shared. So on the page that we just did, so if you had 2 dots between your 2 symbols, that was a bonding pair. And then the lone pairs, and that's a pair of electrons on an element that isn't being shared. So for instance, the chlorine had 3 lone pairs around it because those weren't between, but you had the one bonding pair between the H and the Cl. Just another thing that is in there that we don't represent with dots are pi bonds, and these are found above and below the nuclei of the atoms. They're weaker, but they're kind of a secondary bond that do affect the shape. Now, this is what is kind of titled, obviously, the summary of VSEPR, and this is how we will determine the shape so that we can actually give them names. And so this first column is just the total number of electrons around the central atom. This central atom is generally going to be the element that you have one of, or it will be the one that has the most electrons to start with. And then the second column are the bonding pairs, and then finally the lone pairs. And so there are 6 basic shapes that we will talk about, that we will go over as far as when we use them. Again, we'll kind of draw them, and in class we'll talk a little bit more about what those shapes look like. They're 3-dimensional, which obviously is hard to do when you're drawing a picture of them, but in the real world they do have a very specific configuration. Okay, so when you are determining the shape, so you determine the central atom, usually one of them, you draw the Lewis dot structure, you determine the number of bonding pairs and lone pairs, and then you use that summary sheet to determine the shape. So if we go back and we do NH3, so NH3, so we've got N, and we'll put it in the middle, and so this, you can look back, and we've already done this one, so I'll just draw it real quick. And then it's got the 3 H's, H, H, and H. Okay, so now you have our Lewis dot structure. So then determine the number of bonding pairs. In this particular compound, you have 3 bonding pairs. They are the ones that are between the hydrogen and the nitrogen. So there's a bonding pair, there's a bonding pair, there's a bonding pair. And then you have 1 lone pair, and that is this pair right up here that is on the nitrogen as part of the configuration, but it's not affecting, or it's not bonding it to anything else. So then if you look at your little summary chart over there, we have said that we have, I know it's kind of small on here, but you have 3 bonding pairs and 1 lone pair. So the shape for this compound is trigonal, or this molecule, trigonal pyramidal. And I'm going to pyramidal. There we go. All right, so pretty straightforward. That essentially means that you have that lone pair is pushing all of the other electrons kind of away from it. Remember, negatives repel negatives, and so it's almost like a tripod setup. So with the H is forming kind of the legs of the tripod, and the lone pair sitting up there at the top, like where the camera would be if we're thinking about the tripod situation. So very straightforward. Again, this is a chart that you will always have, and you don't need to memorize it, you don't need to do that, but I want you to use it well. Okay, so now the second characteristic that is important for compounds or for molecules is polarity. Polar molecules are ones that have a slightly negative end and then a slightly positive end. So, and there are 2 conditions for being polar. You have to have a bond type that is polar covalent, and you have to have an asymmetrical shape. On the chart, and we'll mark this together in class, but on the chart, the bottom 3 shapes are asymmetrical. So the trigonal pyramidal, which we just talked about with NH3, angular, which on the picture looks kind of like this bent shape, and then the bottom one, which is 2-element linear. So they're just form a line. And so those are asymmetrical. Okay. Now, we're almost done. Whew. State of matter. So solid, liquid, gas is what we're talking about here. So first thing you have to do is determine the type of compound, and this is based on the bond type and the type of shape, symmetrical or asymmetrical, and kind of some criteria. I will have you write this information down on your chart so that you again will use it as a reference. But first things first, so to be a nonpolar molecule, there are two possibilities for being nonpolar, two sets that you could have. First off, you could just simply have the nonpolar bond, simply have the 0 to 0.4 difference between your electronegativities. And if you've got that, it's nonpolar. Or you could get a polar covalent bond type. You could get 0.5 to 1.6, but you also have to have a symmetrical shape, which are the top three on that chart. And again, we'll mark those. So two possibilities for being nonpolar. Polar, we just talked about. Polar have the 0.5 to 1.6 electronegativity differences, so that type of bond, and then the asymmetrical shape. So that's the ones that we listed, the bottom three on that chart. So that's polar. Or ionic. To be ionic, you simply have to have an ionic bond. And so again, you have this kind of criteria that you have to run through to make sure you know kind of what you're working with. Okay, then, so that was the first step, figure out nonpolar, polar, or ionic bond type. Then you calculate the molar mass of the compound, and this is done by adding up the mass numbers. And so here is the third chart that you will be using for this whole process. So, and then you use that. So NH3, it's kind of our go-to example. We said that NH3 looks like this. So here's N in the middle and your H's all around it. All right, and then we said that we had 3 bonding pairs and 1 lone pair, which gave us a trigonal pyramidal shape. So we've known this so far. Now, the other thing, and I would probably, if I were you, go ahead and mark this as an asymmetrical shape. So we have that already kind of on our minds. Now, so this is what we already have talked about, and so we've kind of got part of the puzzle. Remember to figure out, excuse me, first thing you really need to figure out is the bond type. So for nitrogen, if we're doing electronegativity values back to that first chart, then you would subtract 3 for the nitrogen minus 2.1 for the hydrogen, which gives you 0.9. All right, so according to that, that is a polar covalent bond type. And so remember, going back to the page before, to be nonpolar, you either have to have nonpolar bonds, which this doesn't, or you can have the polar covalent bond with the symmetrical shape, which we don't. So now if you go, to the second thing, the polar molecule, you have the polar covalent bond with the asymmetrical shape. So that's kind of our next step, is we know that we have a polar molecule. And so now we're to the point where we can get to this adding the molar mass. So on the periodic table, each element has a mass number, and you have the decimals there. I personally always tell my students, just round it to a whole number, so you don't have to worry about all the decimals. So if we're looking at nitrogen, nitrogen's mass number from the periodic table is 14.01, so I'm just going to put 14. Hydrogen's is 1.01, so for each hydrogen, so this time I have to look at each hydrogen, I have 1 plus 1 plus 1 because there are 3 of them, and I get 17. So now if I look at this little chart up above, I know I'm looking at a polar molecule. It's not going to be a gas because they aren't gases, But then look on that middle column for the liquid, it says molar mass between 0 to 100. So we're looking right here. So because we're in that part, we know that our final answer essentially to all of this is that this substance is a liquid. So all that just to figure out I have a liquid. Excuse me, man, that makes me really emotional apparently. Okay, whoos, wowza. And that's it. That's all you got to do, kids. So anyway, so like I said, we obviously will go through lots of practice on this in class and go through more of the examples from this also in class. So let me know if you have questions. Be in class, which will make it a lot easier. We can go through stuff, but if you're using this video, of course, always feel free to let me know if I wasn't clear. Thanks, guys. Bye.